Okay, so today we're going to look at implicit differentiation. So this is a type of question that appears in the Analysis and Approaches HL papers. So you have to be able to know the difference between what an explicit function is and an implicit function. So an explicit function is basically where your x and y variables are separated onto opposite sides of the equation, whereas your implicit function is where your x and y's are not separated onto different sides of the equation here. So this one you have to be able to recognize for these type of questions. So a curve C has an equation of 2 to the power of x plus y squared equals 2xy, and they want you to find the exact value of dy by dx at point or the coordinate 3, 2. So if you want to differentiate 2 to the power of x, you need to remember the general form of when you're differentiating an exponential such as a to the power of x, you take the natural log of the base and you times it by a to the power of x again. So in our scenario here, we have 2 to the power of x. So if I differentiate that, I take the natural log of its base, which is 2, and times it by 2 to the power of x again. So if I tidy it up, I end it with 2 to the power of x, the natural log of 2. So the next part I'm looking at is differentiating y squared. Now I can't differentiate that in term with respect to x because it's expressed as terms of y. So I can use the chain rule, however, and try and differentiate with respect to y. So du over dx is equal to du over dy times dy over dx. So we're going to let our u in this scenario be y squared. So let's pop that back in. So I end up with dy squared dx dy squared over dy times dy by dx. So basically what you're doing is differentiating with respect to y, and then you got to times it by dy by dx. So if I differentiate y squared, I end up with 2y and then times it by dy by dx. And the next part we're looking at then is differentiating 2xy. So here we've got a term in terms of x and y, so I need to look at using the product rule here. So in this case, I'm going to let u equal to 2x and v equal to y. Du over dx is equal to 2. And dv over dx is going to be, so we've got a y here, so differentiating with respect to y, so y differentiate is 1, and then I don't forget about to times it by dy by dx, so I actually end up with just dy by dx. So the product rule states that v du over dx plus u dv over dx. Okay, so in our case here we've got v as y, and then du by dx is 2, so 2 times y, I have 2y, plus u, which is 2x, and our dv by dx is dy by dx, so 2u times dy by dx is what we have here. And then now I'm just putting them all together. So the differentiated form of 2 to the power of x is 2 to the power of x natural log 2. And then I have y squared differentiated is 2y dy by dx. And that equates to the differentiated form of 2xy, which is 2y plus 2x dy by dx. And now I'm looking for the exact value at the coordinate point 3, 2. So I'm going to substitute 3 for all of my x values and 2 for all of my y values. So I'll have 2 to the power of 3 natural log of 2 plus 2 times 2 dy by dx is equal to 2 times 2 plus 2 times 3 dy by dx. Simplify and tidy it up. So 2 to the power of 3 is 8, so I have 8 natural log 2 plus 4 dy by dx is equal to 4 plus 6 dy by dx, and because it's looking for the exact value of dy by dx, I want to isolate that, so I'm going to take all my dy by dx terms onto the right hand side and everything else I'm going to put onto the left hand side. So I should end up with 8 natural log 2 minus 4 is equal to 2 dy by dx. And because I want just dy by dx, I'm going to divide everything by 2. So I should overall end up with dy by dx is equal to 4 natural log 2 minus 2. And that should be the exact value of dy by dx at the corner point 3, 2.